Hey everybody, today we're talking about bivariate distributions focusing on the discrete type. We're in a situation where we have a couple of random variables, x and y, which right now we'll assume to be discrete, and we're interested in probabilities of different combinations of their values. In other words, we want to know their joint distribution. When little x and little y are particular values of those random variables, the probability that x is equal to little x and y is equal to little y is called the joint probability mass function, and we typically abbreviate that f of little x comma little y. For instance, suppose we have two random variables x and y with this joint distribution. So here I'm just writing their joint distribution using a simple table. The probability that x is equal to 2 and y is equal to 3 is just f of 2 comma 3. I identify that entry in the table. It is 7%. We compute probabilities of more complicated events by adding individual probabilities. For instance, we can find the probability that x is equal to 2 or y is equal to 3 by adding up the probabilities for all the different outcomes where x is equal to 2 or y is equal to 3. That means f of 2 comma 2, f of 2 comma 3, f of 1 comma 3, and f of 3 comma 3. Identifying those entries in the table, adding up their probabilities, we get 46%. For any joint probability mass function, f of x comma y, we need to have three properties. First of all, the probability that you get, the probability mass, has to be between 0 and 1 inclusive. And that makes sense just from your basic properties of probability. Secondly, all the values of the joint probability mass function have to add up to 1. Again, basic probability axiom. Finally, for any event contained in the sample space, you can get the probability of the event by adding up all the individual probabilities of the outcomes in that event. The distributions of the individual variables can each be determined from the joint PMF. These are called the marginal probability mass functions, and they're abbreviated f sub x of x and f sub y of y. So each of these are representing mass functions for individual variables. And we get them just by summing up over the opposite variable. For instance, f sub x of x is the sum over y, so for all the y values that are in the support of y, of that joint PMF. For instance, going back to the same example that we've been looking at, f sub x of 3 is obtained by summing up f of x comma y with x equals 3 over all the possible values of y. So in this case, I'm doing f of 3 comma 1 plus f of 3 comma 2 plus f of 3 comma 3. When I do all that arithmetic, I get 27%. Again, I'm keeping the x value of 3, adding up over all the possible values of y for that x value. Since we can do this for every value of x and every value of y to get our two marginal probability mass functions, it's natural to add all of the marginal probabilities to the joint probability table. So I've done that here. One check on the work here is that if you add up either of the marginal probability mass functions, you should get 1. Basically, each of the marginal probability mass functions is a legitimate probability mass function, so it should obey all of the axioms, including adding up to 1 when you sum over the support. Two random variables, x and y, are said to be independent if f of x comma y is always equal to f sub x of x times f sub y of y. Sometimes we say that the joint probability mass function factors over the marginal probability mass functions. If this equality fails for even one pair, x comma y, then we say that the random variables are not independent, or we just abbreviate that by saying that they're dependent. For instance, the random variables in this example that we've been working with throughout this vid are not independent. And you can see that, for instance, by looking at the values x equals 1, y equals 2. f of 1 comma 2 is 0.12, while f sub x of 1 times f sub y of 2 is 0.17. And so obviously 0.12 is not equal to 0.17. Let's do another example here. Suppose x and y have the following joint PMF. f of x comma y is equal to c times x squared y, where c is some unknown constant. It's going to be our job to find it. And the support here is just 5 sets of ordered pairs. So first we find c, and then I want to compute the marginal probability mass functions f sub x of x and f sub y of y. Finally, we're going to want to determine whether these two random variables are independent or not. So I recommend pausing the video here, trying this on your own before proceeding to see my answer. So the probabilities all have to sum to 1. So what I'm going to do is I'm going to plug in all 5 of the ordered pairs that are in the support here. I'm going to add all of those up. I'm going to set it equal to 1. Each one of those individual probabilities has the unknown constant c in it. So when I do add all that arithmetic on the right-hand side, I get 38c. 38c equals 1 implies that c has to be 1/38. So the joint probability mass function is 1/38 x squared times y. Let's determine f sub x of x. And we're going to do that just by repetition, basically. For each of the possible x values that are in the support, we are going to sum over all the possible y values. So for instance, f sub x of 1 is f of 1 comma 1 plus f of 1 comma 2. We get 3/38. Similarly, you can check that f sub x of 2 is 8/38 and f sub x of 3 is 27/38. Similarly, for the joint probability mass similarly for the marginal probability mass function of y, we get f sub y of 1 is 10/38, f sub y of 2 is 28/38. Here are all those results summarized in a more efficient form. Again, we can check our work by verifying that in each case the probabilities all add up to 1. Now, if these two random variables are independent, then the joint probability mass function should always equal the product of the marginal probability mass functions at the appropriate values. However, in this case, f of 1 comma 1 is 1/38, and f of x of 1 is 3/38, f of y of 1 is 10/38. And the product of f of x of 1 times f of y of 1 is not the same as f of 1 comma 1. So again, all it takes for the two random variables to not be independent is that this equality fails for at least one x comma y, and that's the case here. So we can conclude that these random variables are not independent. They're dependent on one another. One very useful fact is that if x and y are independent, then the support of x has to be the same for every y value, and the support of y has to be the same for every x value. That's just a long-winded way of saying that the joint support of x comma y, has to be a rectangle. The proof is really direct. If you have a value that's in both the support of x and y, that means that the marginal probability mass function at that value is non-zero in each of the two cases. And that means the product has to be non-zero. So that means the joint probability mass function at those two values has to be non-zero. So basically, we're getting that joint support is a rectangle just very directly. This gives us a quicker way to verify that the variables in both of our two examples are not independent. And I think that's most apparent from the table here that we did with our first example, but you can also see it looking at the support in our other example where we had c times x squared times y.